All right. Hello, everybody. Good afternoon. It's a great pleasure to be here. Thank you for the organizers for giving me the opportunity to talk here. And apparently, I didn't even manage to change my opening slide. But this is my apology for the 3 people that were at this conference 2 weeks ago, that this will not be new to them. Okay, so I want to talk about 2 polytopes, which are related. I will start with the geodesic flow on the round sphere, so very simple object. To get something more interesting, I will use separation of variables. The space of systems that you can get by separation of variables on the sphere has a very nice structure, which was actually found by Sasha Veselov and Konrad Schöbel. This is a Stashev polytope. This works in n dimension, and I will say a few words about larger n, but mostly I will work on S3. So this is the space of all systems in which you can separate variables on the round sphere. So I'll call this my moduli space. So this is my first polytope. And I want to understand what happens when I move around in this polytope, what kind of integrable systems I get. So where is the integrable system here? Well, if you have separation of variables, you have an integrable system because you can write down actually your separated 1 degree of freedom system. So locally, it seems very simple. Globally, it's a bit more interesting. So what I want to do to get interesting integrable systems, now I will do reduction. I have the geodesic flow up here, and that gives me a free S1 flow, right? The geodesics are just great circles. And I want to quotient by these and fix the energy. Then I end up on a Grassmannian, which is just the space of all closed geodesics of my system at fixed energy. And that turns out to be S2 cross S2 if you start on S3. And now my second polytope is when I define a momentum map from my integrable system into the image of that map. This will be a somewhat unusual momentum map, and I will explain it. But the main point here is that we use this unusual momentum map. Then the image of that map is a triangle, and it does not change when we change the integrable system. There is structure in this polytope, which I will explain, which is kind of inside, and that structure changes, but the image of that map is constant. Somehow this is supposed to be sound like convexity theorems for toric actions, but there is no toric action here, except for 1 point in this polytope, there is actually a toric system, and I'll come to that. Okay, and well, if there's time, I'll talk a little bit about quantization. And about the joint spectrum, which naturally lives inside this polytope. Yeah, sure. Well, you get a Stashev polytope, but in higher dimensions. Well, you get a 2 Grassmannian, but not from R4, but just higher dimensional Grassmannian. And this will not be a simplex, but it will be, well, it will, this is a simplex, and the image of this map will again be a simplex of higher dimension. But anyway, this will be slide 27, I think. Okay, so let me first explain what is a Stashev polytope, somewhat unrelated to integrable systems, of course, or totally unrelated. It's also called a sociohedron. And it's defined in the following way. So a vertex of this polytope corresponds to a way of inserting n-2 pairs of parentheses into n objects. And so you insert them iteratively so as to resolve ambiguity if you don't have associativity. Right? And so if you have 3 objects, well, you can group the first 2 or the last 2. And those are all ways that you can create pairs. When you have 4 objects, here are the 1, 2, 3, 4, 5 ways of inserting 2 pairs of brackets into 4 objects. And you could start by inserting the inner bracket and then do the outer bracket. And then the inner bracket is just considered as one object. And if you keep going for NS5, you get 14 vertices, which is the Catalan number. One of the things that the Catalan number counts is exactly the number of plain binary trees, which is exactly what we're doing here. So those are the vertices of our objects. Now we have to define what are the edges. And so an edge is a possibility to go from one to the other by applying the associativity rule once. And so these two here are related by an edge. And so that tells us that K3 is a line segment. So that's a relatively boring Stashev polytope. But the first one that's interesting is K, which is the pentagon. K5 is a polyhedron with 9 faces. And so in general, it's an n-2-dimensional polytope. And probably, well, I don't know. If you go to Wikipedia, this is actually a movie. Looks a bit nicer. Didn't make it into my PDF file. But here is K5, 9 faces, 21 edges. So these are 5 gons and 4 gons, 3 4 gons and 6 5 gons. Looks a bit like these are regular, but they're not quite regular. So very interesting objects. But anyway, I will talk about K4 and not about K5. Okay, so the connection from these bracketed expressions to plane trees is just illustrated here. So let's say when you have these 2 pairs of brackets here, 1, 2, and 3, 4, you can represent that as a tree of how you would create these operations, right? First 1 with 2, and then 3 with 4, and then the results of those are the edges of that tree. If you're in the middle, there's no bracket at all. So this is just a tree with 4 legs, right? Rooted planar tree. And these are the other options. I will mostly, to illustrate what is going on, focus either on the generic case in the middle or on the simplest case at the top. And then you have to do the other cases by kind of generalization or specialization, in fact. Okay, so where's the SN? Where's the sphere here? And separation of variables. So it really goes back to Jacobi when he invented elliptic coordinates or spheroconical coordinates, I guess, if you do it on the sphere. Interestingly, I noticed that Lamé did the quantum case earlier. He was interested in the heat equation, separation of variables, but so this was done earlier than the geodesic flow. Right? Then the story continues, Neumann, Steckel, Levi, Civita, Eisenhardt. I don't really have time to go into the history of separation of variables. I will talk a little bit about Steckel, a little bit about Eisenhardt. But the modern story really starts with Kalnins and Miller, which came up with this combinatorial description of separation of variables, which is essentially these trees that I showed. But then a more global theory started with Benenti, and he understood somehow that separation of variables is related to existence of Killing tensors, which commute in our usual sense of their Poisson brackets. So a Killing tensor is just a quadratic integral, an integral that's quadratic in momenta. And if you have that, then you can compute Poisson brackets. You can define what it means to be a Killing tensor in that language and what it means for them to have vanishing Poisson bracket. And in that context, I guess this is already connecting to Alexei's talk in the morning, Nijenhuis property appeared for the first time, I think, in this context of separation of variables, that Benenti understood that these Killing tensors actually come from one single object. So you don't need to know n Killing tensors, you just need to know one Nijenhuis tensor, and from that tensor, you can construct these other ones. Magritte related this to bi-Hamiltonian systems, and Bolsinov and Matveyev to projectively equivalent metrics. So all these stories are nicely related. But I'm jumping to the end here. As I said, Schöbel and Veselov in 2015, they looked at these equations for these killing tensors to commute and then observe that this was actually known from a completely different field where this modular space was understood and turns out to be this Stashev polytope. Well, so that's separation of variables in a nutshell, the history, but I will just do it classically as Jacobi did it in a minute. Okay, so these separating coordinate systems, here are some names that you can attach to them. These are elliptic coordinates, so these are Jacobi's coordinates. And on the boundary of and the edges of this polytope, you find degenerations of elliptic coordinates. These degenerations are not necessarily easy to do, but they're also not hard to do. So all these can be thought of as special cases of elliptic coordinates. If we look at the corners, there's spherical coordinates, different versions of spherical coordinates. And this I call cylindrical. It's also called polyspherical. I'll talk a bit more about what this actually is. Yes. Yeah, I'll come to that in a second. I mean, you can separate the Hamilton-Jacobi equation for the geodesic flow. Yes, I'm starting with the geodesic flow on the three-dimensional sphere. And I'm saying for each point in this polytope, I have a way to separate the variable, separate the Hamilton-Jacobi equation, and that will give me integrals. I'll come to that. I'll hopefully answer that in a little while. Here we go. Okay, so geodesic flow on S3. So I already said the great circles are the geodesics, and so X and P are points in R4, and the length of X, that's my sphere. And I also normalize the energy to constant value. And the square root of H generates an S1 action. It's not H itself because that doesn't have constant period, but square root of H has constant period. So that's a generator of my S1 action. I will not look at energy 0, so there's no problem with the square root. And this is the S1 action that I'm going to divide out. Okay. So now I'm looking for invariants under this action. And the invariants you can write down, they are just given by X wedge P. Or if you want to write this as an antisymmetric matrix, you write X transpose P minus P transpose X. So this is a matrix in SO4. And the claim is that all entries of this matrix are invariant under this flow. Right? And that is, that's quite easy to check. That's an exercise. Well, if you want to write it this in components, then this is Xi Pj minus Xj Pi. And this is, if you want, your standard angular momentum, right? But now there are 6 of them. The rank of this matrix is only 2. And in general, it could be 4, but it's only 2 because we started with this geodesic flow. So these are also known as Plücker coordinates. All right, I'm writing down the integrals now. It's not clear how that's related to separation of variables yet, but any function of these invariants is, of course, an integral. Right? Why? Well, because they are constant under the evolution, and so I could write down any function. But what I'm interested in is functions that are quadratic in momenta, because that's the connection to killing tensors, if you want. So I'm writing down these special quadratic functions in these L. So for each I here, so there's I'm writing down 4 integrals. They're not all independent. Of course, they sum to 0, for example. And I'm introducing now 2 polynomials here. If I sum these integrals up in this way, then I get a ratio of 2 polynomials, and R and A, and these have constant coefficients and they're quadratic in these Lij's. Okay. So let me do the reduction in the first way, which is basically just observing that these Lij's have a Poisson bracket, and that's just the Lie Poisson structure of SO4. And so I can now say my reduced space are the congruent orbits of SO4, and those are exactly the Grassmannians of oriented 2 planes in R4. And that happens to be S2 cross S2. So the upstairs integrable system has, oops, what are my F's? Sorry, I may change the notation here, I guess. So pick two of these integrals here, of these U's, and together with the Hamiltonian, that's the integrable system in the sense of Liouville-Arnold, right, on T star S3. And this descends now to an integrable system downstairs, well, because it's written in terms of invariance, right? So everything is written in invariance. So I get a downstairs system. And here they are, G1 and G2. These are the two commuting functions. Right, so you could just start at this point and say, start with the Lie-Poisson structure on SO4, write down these two functions and check that they commute in that bracket. Right? That's my integrable system. And it depends on 4 parameters, E1, 2, 3, 4. Okay, so one remark on the general case. So you get n-1 quadratic integrals on this larger Grassmannian. And this is simply a special case of the Markov top. It's special because the rank of this matrix of angular momentum is 2, right? And in general, for the Markov top, it's not 2. There's a beautiful article also by Moser about the Lux representation of that system. I wanted to mention Komaras, Kuznetsov, and Zin and Zielinski, who looked in more detail at that system. Okay, so just a little digression. How do you see that it's S2 cross S2? There are many beautiful ways of seeing this, but this is a very simple, explicit way of seeing that. So this SO4 Lie-Poisson bracket has 2 Casimirs. And one is just the sum of all the squares of these 6 angular momenta. Let's fix that to 2 times the value of the Hamiltonian. And the second one is this Plücker relation. That ensures that the rank is 2, if that is equal to 0. And that's also the general Markov allows this to be non-zero, but I am fixing this to 0. And now just see these terms here, they want to be combined into complete squares if you add them up, right? And so let's add C1 and plus 2C2, and then you see you get 3 complete squares. And if you write C1 minus 2C2, well, then you get this term twice with a minus sign, and again, it combines into complete squares. Which one? 1, 2, and the last one here, 3, 4, together with 1, 2, 3, 4. And so here are your 2 spheres, right? This is 1 sphere. Now this is a linear transformation to new variables if you want, and then this is 1 sphere, and that's the other sphere. So it's a direct product of 2 spheres. Okay, all right. So now let's remind ourselves what Jacobi did, and hopefully I'll answer your question of what I mean by separation of variables here. So now I'm going to a point that's inside the Stashev polytope. So this is the generic situation. So Jacobi says, look at this polynomial here, Q of lambda, which has the sum of xi squared, and then lambda, this argument in the denominator, minus ei. And says the roots of this polynomial are our new coordinates. And you can show that you always have the right number of roots, that they're separated by these poles. And those are the elliptic coordinates. I'll call them S1, S2, and Sn. So Q of Si is 0. And if you now write your metric for the round sphere in this coordinate system that is defined in this way, then you will see that here it's in the original coordinate system, and here it's in the new coordinate system, that this is, well, first of all, it's an orthogonal transformation, and you get these factors here in your metric. So yeah, so separation of variables. Before we come to that, a little digression, I guess, to Steckel. So Steckel says that if you choose any n by n matrix where the entries in the ith row depend on the ith variable only, and then define the following functions, fi, which are, take the inverse of this matrix and pick out the ij element, sum over j here times pj squared, you get n quadratic integrals, quadratic in p, right, in momenta. And the theorem that he proved is that these are commuting functions and independent. So it's quite a miracle if you want. But the problem is that one of these functions has to be geometric, right? And of course, so it's a local theorem in a way, right? So you can cook up local integrals, but if they correspond to the system that you wanted to separate in the beginning, of course, it's a different question. So let's say F1 is the Hamiltonian of the geodesic flow. And here is the statement. So if you pick this function, this matrix here, in this way, Si to the power j minus 1 divided by A of Si, and A is this polynomial that I defined a bit earlier, which is just a product here, then you will get the Hamiltonian of your geodesic flow on Sn in these coordinate system, and n minus 1 other quadratic integrals. Eisenhardt then showed that that this also goes the other way, so that Steckel systems are one-to-one corresponds to orthogonal separable coordinate systems. Yes, and these quadratic in momenta integrals that you get this way, you can interpret them now as killing tensors if you want. Right? Anything that is quadratic in momenta, like the Hamiltonian itself, where you have the metric Gij, now you have another n minus 1 such functions, and they define these killing tensors. All right, so finally, separation. So the Hamiltonian in this coordinate system is just the sum over momenta divided by these cofactors in the metric in this coordinate system. And the Hamilton-Jacobi equation basically asks to separate this PDE, right, where the S is the generating function of this transformation that we're looking for. And by Steckel, we now know how to do this. I mean, because these functions, by construction, if you write them in the original coordinates, they only depend on one variable, right? So we do get functions that depend on a single variable only. And if you write them out, they're actually very simple. So here are these separated Hamiltonian systems. So here is only a single Hamiltonian system. P squared is this ratio of these two polynomials. But this variable S here can be any one of these S's, S1, S2, S3, it doesn't matter, right? So it's even better, they are all the same. So this geodesic flow on the sphere is really just this single Hamiltonian system, n copies of that. Okay, I just want to mention that you can also separate Laplace-Beltrami equation in the same way. It leads to a Fuchsian ODE. And if I have time, I'll say a few words about those. So that's the story in the middle of the Stashev polytope. Now, if we allow equality of these parameters here, we get degenerate cases, and they correspond to edges and vertices of the Stashev polytope. And so, for example, in this case here, at the top, 1, 2, 3, 4, means you have E1 is E2 and E3 is E4. So it's the double cylindrical, if you want. And in general, you can do this limiting process, and it gets something slightly more complicated. And in quantum mechanics, you start with Fuchsian equations, and then going to these limits means that you have confluence of all of the Fuchsian equation. Okay, I think we've had this before. Let me just briefly explain. For example, this 1, 2, 3, 4 case. So now we have how is a coordinate system associated to this case? Well, here's our tree. And so you write cosine phi 1, sine phi 1 here. The reason is that the sum of squares of these is 1. Then you do the same with another angle, phi 2. Sum of squares is 1. And now you combine these with another angle, right? We have 3 angles on the sphere, cos psi, sine psi. And here's explicitly the coordinate system x1, 2, 3, 4, as they are combined. And then you can check that they, of course, add up to 1, right? So this is the simplest coordinate system, I guess, in a way that is in the Stashev polytope at the top corner. Right? And in more complicated ways, but a similar idea, you can do this all around the vertices and the edges. Yeah.
So So your special polytope is two-dimensional.
Yes.
The two-dimensional coordinates is choice of 5 numbers.
Yes.
How many numbers lie over?
Yeah, so I guess I should have said that. So 2, basically you can, by translation and by scaling, you can get rid of 2, right? So they're not essential parameters, but then there are 2 essential parameters left, and that's the plane that you see of these 2 parameters. No, it's 4, right? So 1, 2, 3, 4, and then
5 minus 8 rejected.
Yeah, 5 minus 3 in some sense is maybe the most natural way. I mean, if you also in particular go to the Fuchsian equation, I mean, then that's how you would count there. Yeah. Okay, here I just want to point out global symmetries that you can read off from basically this pattern here. So if you have 2 pairs like that, it means you have a T2 symmetry, right? Because if you have E1 is E2, you can rotate in the E1, 2 plane, and 3 and 4 are equal, so you can rotate in the 3, 4 plane, right? So this is a T2 symmetry, and that's why this corner is the simplest. Right? If you have these other corners, they are spherical coordinate systems. So they really only have a single free S1 action. And that's why they're not as nice as this one. So this is actually going to lead to a toric system. It's going to be the only toric system that's in this family. And these are toric degenerations. Yeah. So you can think of this as an action on the original space, which is T star S3, but it also descends to the reduced system on S2 cross S2. So, and that's the most interesting case. I really want in the end a T2 action on this S2 cross S2. And here I have S1 actions, while in the middle there's no global S1 action at all. Okay, so I guess that's the tail of the first polytope. So now I'm coming to the second polytope. So I wanted to ask, is there a momentum map with a convex image for this family? And of course, we have this one system in the top, which has a T2 action. So there's a toric action on S2 cross S2, and that will have a Dullin polytope associated to it. But what I want to suggest is a different moment map that leads to this triangle. And if you know Dullin polytope, then you would say, well, triangle is pretty wrong for S2 cross S2 because it's not possible as an image of a toric moment map. And yes, that's true. So this moment map that I will suggest is in a way a folding of that one. Anyway, so I'm motivated by these convexity results, but I understand that they don't hold for every member of this family. Okay. So here's the moment map. It's actually very simple. You just take the actions that the Liouville-Arnold theorem guarantees exist. Of course, these are not global, and that is the problem. But anyway, so here they are. So it just says integrate PDQ over some cleverly chosen cycles. So these are complete hyperelliptic integrals in our case. So this is on a genus 3 curve. And here, this is another story that actually with Sasha, we first saw on the Neumann system. So if you somehow define the cycles after discrete symmetry reduction, then you get a map that is continuous. And that's important for me. I mean, otherwise, this map is kind of essentially useless. If you just use the Liouville-Arnold actions, of course, it will not give you anything global, right? But if you do it in this way, you get something that is continuous. So why is it a triangle? Well, that's also simple to see now. Well, first of all, I mean, you have to observe that the sum of these actions is the square root of h. And that is essentially just the statement that the residue of this integral, of this one form, if you want, at infinity is little h. That just comes about in which these values of the integrals are built into this. And it's a little calculation, but that's the essential property here. Well, okay, now we can do reduction again. So this reduction works on the action variables directly, right? I'm just going to say, okay, let's fix this action. And then there is an S, this is also the S1 action that we want to quotient by. And so we just identify the angle variable that corresponds to this one to a point. And then we get action variables for this reduced integrable system. So instead of J1, J2, J3, use pick any two and the sum. That's a unimodular transformation. And then you do the reduction, and that just gives you J, I, J, J. So for any IJ that you picked. And now we have action variables on the reduced system. And why is a triangle? Well, because now this is fixed and these actions are non-negative. And so this is just a slice of the positive octant. Okay, and now, well, what's the problem? Of course, this it's now a continuous map into this triangle, right? And it's smooth in these four pieces, but it has these lines here along which the map is not smooth, but it is at least continuous. Right? So this is maybe as good as one can expect. It is continuous, it's global, and it maps into a triangle, right? And this triangle doesn't change when you change the family, when you move the system around. What changes are these lines inside, the singularities. And just to give you some illustrations, so this is a joint work with my PhD students, Diana Nguyen and Sean Dawson. And so they looked at all the details of these cases. So if you degenerate vertices or edges of the polytope, then your integrable system degenerates into simpler one. This is the general elliptic case in the middle. And the simplest case is this 1, 2, 3, 4, right? That's this one. It still is a triangle, but it doesn't have any singularities anymore, which it shouldn't, because now we have a global T2 action. But the image is the wrong image because we did this discrete symmetry quotient. And that's why we don't get a square, but instead a triangle. And I'll unfold that in a second. Let's see, how are we doing on time? Too bad, okay. Well, I don't know, do I have 5 minutes? Yeah, yeah, okay. All right, so I think, I hope I explained now, first of all, that every integrable system that is obtained by separation of variables, the geodesic flow on the round sphere, after reduction, has a continuous piecewise smooth momentum map whose image is a rigid triangle. Rigid in the sense that if you change your integrable system on S2 cross S2, this image will not change. The range will not change, but the singularities where the map is only continuous will change. The edges of the Stashev polytope, they correspond to systems that have better symmetry. If you want, they have a global SO2 or SO3 action. And that is upstairs and downstairs. And one of them is semi-toric in the technical sense that doesn't have hyperbolic singularities, which is important for some people, including myself, because there is a good classification theory for these systems. And the corners of the polytope, they correspond to systems which have almost global T2 actions. So one of them has a global T2 action. That's the one at the top corner that I talked about. And then the other one that are spherical coordinates, they are only almost as good. They are toric degenerations. And I think Alexa and Sasha had recently a PhD student that worked more on that. Okay, so a few words about higher dimensions. So I guess I'm answering your question again. So if you start on Sn, then T star is n dimension 2, and the space of geodesics is this Grassmannian. Again, it's just a higher dimensional Grassmannian, but it's still a 2 Grassmannian. Separation of variables in the same way gives integrable systems on this reduced on this orbit space, and so we get integrable systems on this Grassmannian, And these are integral systems where each integral is quadratic momenta. And the modular space of all of these will again be a Stashev polytope of higher dimensions. And again, this Liouville-Arnold actions work in the same way. So we can write down an image, a momentum map that maps all of these systems into an n-1 simplex. And that image will not change. Again, what happens inside the image will depend on your moduli, on your chosen system, but the range is fixed. Okay, so the last few minutes, I'll talk a little bit then about the quantum setting. And here we'll also come to the relation to the standard toric action, and it's whose image should be a square, not a triangle. So first of all, the eigenfunctions of this system are very nice and very well known. They are harmonic polynomials. So meaning polynomials that satisfy Laplace equation Rn plus 1. Because they restrict in a nice way to Sn so that they give eigenfunctions on Sn. And so for fixed degree of these polynomials in n plus 1 variables, they form a vector space. And in a way, these integral systems that we constructed now, they are the classical analogs of these harmonic polynomials, or of versions to write, well, to choose a basis in this vector space, I guess I should say. So since the round sphere has so many symmetries, these eigen values are highly degenerate. So an energy eigenvalue for this for the upstairs system has this degeneracy, and with multiplicity with this. Sorry, these are the eigenvalues, and this is the multiplicity of the eigenvalue for n is 3. Right, so they have very, very high degeneracy, and if you restrict these harmonic polynomials to the sphere, then you get spherical harmonics, right? So this is also related to this star, of course. Yeah, and this is what I said. So this the joint spectrum of our integral system on S2 cross S2 gives a basis for these harmonic polynomials, different bases depending on the parameters. So quantum also has a relation to special functions, and I want to briefly mention that here. So you can represent the commuting operators now as Fuchsian differential equations. And the quantum states are the polynomial solutions of these equations. And these Fuchsian equations, they have finite regular singular points at the zeros of A. So these are E1, E2, E3, E4. So that's the 4 parameters, but the Fuchsian equation also has a point at infinity. So that would be, if you do it projectively, these 5 singular points. But I'm only counting finite regular singular points here. That's my abbreviation, FRSP. So if you have 2 finite regular singular points, you have the hypergeometric equation. If you have 3, you have Hoyne equations, and then the names run out. And I'll show you the Stashev polytope from this point of view in a second. And the pictures that I'm going to show you now, they show the joint spectrum of these commuting operators in the image of the momentum map, which is a place where they naturally want to live. So here, when there's a 2 here, those are hypergeometric equations. So the corners, the quantum system are a hypergeometric equation. At the edges, it's the Hoyne equation, and inside, it's one more complicated than the Hoyne equation. Okay, so here is the simplest case, 1, 2, 3, 4. So here we have a global T2 action. So in my Liouville-Arnold action map, I always map into the triangle, right? But the multiplicity of the points in this triangle is unusually high now. It's 4 inside and it's 2 on the boundary, right? And we call this joint spectrum origami. So what we should do is take this triangle and unfold it twice so that every state is represented by a single dot instead of eigenstate being represented. Well, these dots here represent 4 dots, 4 eigenstates, 1 dot. And if you unfold twice, then you get the image of the momentum map that you maybe expected, which is the square which is the Dullin polytope, which you should get when you have a toric action on S2 cos S2. Right? But this is not stable, right? If I now change my parameters of my system, this picture doesn't survive, right? But this one does. And so that's why we like this one. So for example, here's a semi-toric system without hyperbolic points, where there's just a singular point on the boundary here. This is a focus point. And again, there's multiplicity in this picture, and you can unfold once. And if you do that, you get this semi-toric polygon. So in this classification theory, semi-toric systems, there are also polygons, polygon invariants. They're not necessarily convex, and they have this one special point, but we will cover those as well. Oh yeah, and I guess I forgot to mention this. Yeah, so I talked about multiplicity. So you see always in these pictures 21 squared dots, right, which is the number of harmonic polynomials of degree 20 on the sphere. And you could do this for any degree, of course, right? So you get a whole family. Okay, so toric degeneration. Again, so in this picture, there is one singular point here. You can't even see in the picture that this is a singular point. But if you, again, unfold once, it stays a singular point. And that's, again, this is why this is not a Dullin polytope, because we actually don't have a global T2 action. So there's a T2 action everywhere except at this point it fails because the vector field is actually not defined for that point. Okay, and now more general cases on the edges can have hyperbolic singularities and they unfold into these more complicated pictures. Maybe I'll just finish up. So separation of variables gives an interesting family of integrable systems on compact symplectic manifolds. And they have a moduli space, which is the Stashev polytope. And I showed you some pictures of these for n for the 3-sphere, but it works in n dimensions. So in 3 dimensions, this family contains toric, semi-toric, toric degeneration, hypersemi-toric. I guess this is a notion that Sonia introduced, and more general integral cases. And so my hope is also, I just presenting an example, I guess, is to say, well, here's an interesting case that of a family that lives on a compact symplectic manifold for which this classification theory does not at the moment work. It works on the boundary, but it doesn't work in the middle, right? So it would be interesting to see if it can be made to work. Yeah, it works in higher dimensions. And there's also, well, this interpretation, which I like. So the quantum case, in a way, is understood very well. And it leads to all a zoo of special functions, which has been studied for a long time. But to my knowledge, in a way, to write down the classical analogs of these special functions, it's the first time that what we've done. And so in a way, this could be interesting to study, for example, the high quantum number asymptotics of these special functions. Okay, and with that, thank you very much for your attention.
From my side point of view, what you do, you start with a standard genetic flow on the sphere, which has 4 pointed flows. I choose some special integrals corresponding to special Lagrange operation. Then you quotient by the action of the sphere and then to go to the level Z, so it makes a sphere reduction. And then you work with the system. In particular, you study action angle variables for the system. Yeah, action variables, right?
Yeah.
Why you did not look for action variables for these integrals on the initial system? Why you do first quotient and then and not first action variables and then quotient? It shouldn't be competitive.
Yeah, so I mean, you're right. The actions variable that I wrote down, J1, 2, 3, they are the action variables for the upstairs system, right? But in a way, the upstairs system doesn't have unique action variables, right? Because I mean, there's all these choices, right?
What the choices?
Well, I know, but I could have chosen any other point in the Stashev polytope that would have given me action variables for the upstairs system. Right? So from my point of view, so doing the quotient, I end up with a system that is smaller. And I guess, yes, the Hamiltonian disappeared. But for that system, those action variables, well, up to permutation, I guess, which two you choose, are essentially unique.
So second, why they're not unique for the upstairs system?
Because any way of separating variables on the upstairs sphere gives you a choice of action variables.
But you also here you choose the point of the way of separation of variables.
Yes, that's right.
So what's the difference?
Well, if I chose a different point, it would give me a different set of actions for the same system on the round sphere, right? So, but after I quotient, so I pick the point in my Stashev polytope, and then I quotient, then I get a reduced system, and for that system, I don't have a choice of action variable anymore.
Right? The quantum system to sphere is one, and you do not
sphere. It's too symmetric, right? And so in some sense, right? And so you make this choice that induces an integrable system of lower dimension, but that is, well, obviously less symmetric, right?
May I ask one more stupid question? Yeah. So for me, coordinate is just some coordinate system, and the coordinate system where the metric is diagonal to this coordinate system. Downstairs there are polynomials to support xi minus xj for the over j, and upstairs there is a polynomial of degree n plus 1. Yeah. So in your
right.
case, the polynomial staying upstairs has real roots. Why?
This is special property of sphere. Constant negative.
No, the curvature of the guy is the highest leading term of the polynomial staying upstairs. It doesn't depend on the limit.
No, the highest term is the Hamiltonian.
No, I'm speaking about the how the negative sphere moves in the elliptic coordinates.
Yeah.
And the freedom you can do there is a choice of polynomial of degree n plus 1 until comes a spectrum. Polynomial of x1 comes to near dx1 square, polynomial of x2, the same polynomial comes near dx2 square, and so on. Yeah. And so we have complex roots. Why do you don't have
Special property of sphere.
No, sphere is positive.
Positive curve.
It's positive.
But I'd like to mention that, this is the geodesic flow on sphere, talking about special level. You always think that, level of integrals must be taught, right? I look at this. In this case, if momentum is 0, then you have just sphere itself.
Yeah, which is excluded in this case, right? Yeah.
It's a kind of surprisingly, it was for me that, such simple object like geodesic or surface flow on sphere, which is on Torsten geometry number 1, right? Gives so much interest in mathematics. By the way, one thing I'd like to mention is that you mentioned Kalnick, but I think it was Vilenkin who used this he called it
polyspherical, yeah.
And it related to representation theory. It's not very well known, I think, this fact, but it's hidden in the book.
Yeah, there's a singular point. Yeah. But you had another question. Right?
So we are looking at systems. Now, of course, we've got as the 4 actions.
Yeah.
Here. But we've got a momentum map taking to pull up the algebra. So are they actually all coming from?
Yeah, that's where they live. So the reduced system live on these co-adjoint orbits. Yeah.
Thank you very much for very interesting talk. I just wanted to ask you one thing. Respective systems, that's they come from very special separation relations. Any general separation relation, generalized theory,
yeah, I mean, in some sense, you could say, I'm not sure if that's the direction in which you're thinking, that any superintegrable system, right? I mean, people looked at adding potentials to this, and that would work, right? I mean, yeah.
By separation relations that are quadratic in momentum, that are linear or affine Hamiltonians, and then you get the system. But look at this, you keep up with these assumptions, you make any separation relation. Or, for example, separation relations coming to the single separation curve. Still obviously, but with this system.
Right. To be honest, I don't know the answer. And it would be interesting to discuss. At the moment, it seems very particular to have these quadratic integrals, right? But maybe you would, if you do it on a more general curve, you might get more interesting integral systems, right? Yeah.
And last question. I mean, it is very nice, of course, that you get this Polytopes and you have this all steps in this very different. You don't gain any knowledge about the original system.
That's certainly true, yeah. But my claim is that you do gain knowledge about the special functions that that you obtain also separation of variables. Right? This is kind of the semi-classical or the classical analog of these special functions. Yeah. But I totally agree. Of course, I mean, we reduced it by the Hamiltonian, so you don't learn anything about the original geodesic flow. Right? Thank you. That's the right answer. Yeah.
You know, your curves all actually right?
Mm-hmm.
But you actually freedom of curves, you know, but the expected theory and the theory that they always consider quadratic momentum. Actually, it's not required.
Yeah, that would be great. That's it. Yeah, no, yeah. No, I think that is special to separation of variables with quadratic integrals. Yeah. But the second part may work. Yeah.
Thank you very much.
My native way.